Welcome, my name is Dr. DrWedding, and this is DrWedding, DC25. Norton Equivalent Circuits. In this video you will learn what Norton's theorem is and how to use it to easily convert any circuit into a Norton equivalent circuit. A Norton equivalent circuit should not be confused with a Thevenin equivalent circuit. Thevenin circuits were covered in the previous video. Norton's theorem states that if you have a linear circuit made up of voltage sources, current sources, and resistors, it can be converted to an equivalent circuit made up of one current source and one resistor. So, the circuit on the lower left can be converted to the parallel circuit on the lower right. The original circuit and the equivalent Norton circuit will always deliver the same power to the load. For example, if the load resistor is 1 kilo ohm, then the voltage across the load in the original circuit and the Norton circuit will be the same. The current through the load will also be the same in both circuits. If the load resistance is increased to 10 kilo ohms, the voltage across the load and the current through the load will be the same in both circuits. If the load resistance is increased again to 15 kilo ohms, the voltage across the load and the current through the load will be the same in both circuits. The original circuit and the Norton equivalent circuit will always deliver the same voltage and current to the load. Because power is voltage times current, you can also say that both circuits deliver the same power to the load. Converting a circuit to a Norton equivalent circuit only takes 3 steps. Step 1. Find the Norton current. Start with the original circuit and replace the load resistor with a 0 ohm resistor. The Norton current is the current flowing through the 0 ohm load. Step 2. Find the Norton resistance. Start with the original circuit and remove the load resistor, leaving a gap. Replace voltage sources with a wire and replace current sources with an open gap. The Norton resistance is the resistance measured where the load resistor was removed. Step 3. Draw the Norton circuit. Below is what all Norton circuits look like. This is the final answer for all of these types of problems. Norton circuits are so easy because you only need to find 2 values, the Norton current and the Norton resistance. Let's start with a demonstration that will convert this circuit to a Norton equivalent circuit. Step 1. Find the Norton current. Start with the original circuit and replace the load resistor with a 0 ohm resistor. The Norton current is the current flowing through the 0 ohm load. To find the Norton current, start with the original circuit and set the load resistor to 0 ohms. Don't worry, you will always be told which resistor is the load resistor. The Norton current is the current flowing through the 0 ohm load resistor. The easiest way to get this current is to find the current through a resistor in series with the load. In this example, the Norton current is flowing through the load, as well as R5. So, you need to find the current in R5 to generate the Norton circuit. This is a series parallel circuit, and if you feel comfortable setting up a table and solving the circuit for all of the values, you can certainly do that. But it is not necessary. Because we only need one value, a lot of shortcuts can be taken to save time. Start the zipping process by combining R5 and the load resistor. These 2 resistors were in series, so they both have the Norton current flowing through them. There are now 3 resistors in parallel. These 3 resistors are combined into a single resistor. This leaves us a series circuit. We do not need any information about R1 and R3. So using the voltage divider rule, the voltage across R245 and the load can be found. The resistor was broken into its original 3 parallel resistors, and all 3 resistors have the same voltage across them. We only need the current in R5 and the load, so we can ignore R2 and R4. The Norton current can be found by using Ohm's law. Using Ohm's law, the Norton current flowing through R5 and the load is 416.7 microamps. Now that we know the Norton current, we can move on to step 2. Step 2. Find the Norton resistance. Start with the original circuit and remove the load resistor, leaving a gap. Replace voltage sources with a wire and replace current sources with an open gap. The Norton resistance is the resistance measured where the load resistor was removed. If this step sounds familiar, it should. It is the exact same way you find the Thevenin resistance. Start with the original circuit. Remove the load resistor and leave a gap. Next, replace the voltage supplies with a wire or a 0-ohm resistor. Then replace current sources with an open. The Norton resistance is the resistance across the gap. To find the Norton resistance, you need to zip from left to right. To zip this circuit, first combine the series resistors R1 and R3 and redraw the circuit. Then combine the 3 parallel resistors together. This will leave 2 resistors in series that can also be combined. The Norton resistance is the resistance across the gap. And in this example, the Norton resistance is 12 kilo ohms. Step 3. Draw the Norton circuit. The equivalent Norton circuit will always take this form. You just plug the 2 values you calculated into this template. This is the final answer for this problem. Now that you have been introduced to the procedure to create a Norton equivalent circuit, let's try another circuit. If you want to try and solve this circuit on your own, pause the video. When you finish, restart the video to view the solution. Example 1. Find the Norton equivalent circuit for the example shown here. Step 1. Find the Norton current. Start with the original circuit and replace the load resistor with a 0-ohm resistor. The Norton current is the current flowing through the 0-ohm load. Start with the original circuit. Replace the load with a 0-ohm resistor. The Norton current is equal to the current through the resistors in series with the load. To find this current, you will need to zip and unzip the circuit. First, combine R5 and R6 and redraw the circuit. Next, combine the parallel resistors R4 and R5/6 and redraw the circuit. Then combine the series resistors R3 and R4/5/6 and redraw the circuit. Then combine the parallel resistors R2 and R3/4/5/6 and redraw the circuit. We do not need any information about R1, so we will focus on the other resistor. The voltage across R2, 3, 4, 5, 6 can be calculated using the voltage divider rule. This circuit is then unzipped back to circuit C. The voltage across R2, 3, 4, 5, 6 is copied across R2 and R3, 4, 5. To save time and effort, you can ignore R2 and focus in on R3, 4, 5, 6. The current through this resistor can be found using Ohm's law. Then the circuit can be unzipped back to circuit B. The current through R3, 4, 5, 6 was calculated in circuit C. This current is copied into R3 and R4, 5, 6 in circuit B. We only care about R4, 5, 6, and we can find the voltage drop across it using Ohm's law. The 2 volts across this resistor can be copied across the parallel resistors R4 and R5/6 in circuit A. We only care about the current in R5/6 because this is the Norton current. This value can be easily found using Ohm's law. So the Norton current for this circuit is 10 milliamps. Step 2. Find the Norton resistance. Start with the original circuit and remove the load resistor, leaving a gap. Next, replace all the voltage supplies with a wire or 0-ohm resistor, and replace all current supplies with a gap or an infinite ohm resistor. Start to combine the resistors, working towards the gap that was made when the load resistor was removed. Start by combining R1 and R2. These 2 resistors are in parallel. After combining the resistors, redraw the circuit. Now combine the series resistors R1, 2, and R3. Then redraw the circuit. And then combine the parallel resistors R1, 2, 3, and R4. Then redraw the circuit. Finally, combine the series resistors R5, R1, 2, 3, 4, and R6. This gives us the resistance across the gap created when the load resistor was removed. This is the Norton resistance, and it is equal to 800 ohms. Step 3. Draw the Norton circuit. Using the current calculated in Step 1 and the resistance calculated in Step 2, the complete Norton equivalent circuit can be generated. This is the last example in this video. If you want to try and solve this circuit on your own, pause the video. When you finish, restart the video to view the solution. Example 2. Find the Norton equivalent circuit for the example shown here. Step 1. Find the Norton current. Start with the original circuit. Zero out the load resistor. The Norton current is the current through the resistors in series with the load. To find this value, you will need to zip and unzip the circuit. Combine the series resistors R4 and R5. This is circuit A. Combine the parallel resistors R3 and R45. This will generate circuit B. When the series resistors R2 and R345 are combined, circuit C is generated. Because this is a parallel circuit, you know that there is 18 volts across R2, 3, 4, 5. Using Ohm's law, you can find that the current through this resistor is 25 milliamps. This current can be copied back to circuit B. We only care about resistor R3, 4, 5. The voltage drop across this resistor can be calculated using Ohm's law. The voltage drop across this resistor is 3 volts, and it can be copied back to circuit A. When the 3-volt drop is copied across R4, 5, the Norton current can be calculated using Ohm's law. The Norton current for this circuit is 15 milliamps. With the Norton current calculated, you can move on to Step 2. Step 2. Find the Norton resistance. Start with the original circuit and remove the load resistor. Replace the voltage supplies with a wire and current sources with an open gap. Next, we can start to combine the resistors. Notice that R1 is in parallel with a wire. Pretend the wire is a resistor named R0. This resistor is 0 ohms. If you combine R0 and R1, you will find the equivalent resistance is 0 ohms. So when R0 and R1 are combined and the circuit is redrawn, R01 is 0 ohms and is just a wire. R2 and R3 are in parallel, and they are combined and the circuit is redrawn. The final 3 resistors are in series, and they are easily combined. Therefore, the Norton resistance is equal to 400 ohms. Step 3. Draw the Norton circuit. The Norton current from Step 1 and the Norton resistance from Step 2 are used to create the Norton equivalent circuit that is shown here. I hope this video has helped you understand how to generate an equivalent Norton circuit, as well as understanding that the original circuit and the equivalent Norton circuit will deliver the same power to the load resistor. If you find these videos helpful, please like the video, leave a comment, and subscribe to my channel. This is the only way I can continue to make these videos.